right, Math 9, I want to go over any of the homework you had to graph. A few people had some questions, more about the language that was used, I think, than anything else. And then I'll go over the next section, which is actually really fast. So this will not take very long, I don't think. So the ones that asked you to graph were all of these ones. And it said, draw the dilatation image of each line segment under the given mapping. So again, I will do the original and then the final, even though it just asked for the final. So this is not for a shape, it's just for a line, but it doesn't matter. So for number 5, it says point A is 3 and 2. So across 3, 1, 2, 3, and up to 1, 2. So 3 and 2. And point B is 1 and 4. So over 1 and up 4. 1, 2, 3, 4. That's point B, that's point A. So there's my line segment. Okay, it's just a line. You just connect the dots. It wants you to do the mapping 2x to y. So all that means is multiply your x's by 2, multiply your y's by 2, come up with a new point. So for A, if I multiply the 3 by 2, I get 6. If I multiply the 2 by 2, I get 4. So A prime is 6, 1, 2, 3, 4, 5, 6, and 4. 1, 2, 3, 4. That is point A. For point B, if I multiply them both by 2, 2 times 1 is 2, 2 times 4 is 8. So my new point is over 2, 1, 2, and up 8. 1, 2, 3, 4, 5, 6, 7, 8. 2 and 8. So it ends up being 2 times longer than that point. Okay, so this is A prime and this is B prime. Number 6. Oh, that bugs me a lot. 6. Okay, so I did that one a little bit slower. I'll do the next one a little bit faster. Maybe if I can get the cover off. Number 6 says point C is at 6 and 4. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. 6 and 4. And point D is negative 2 and 2. So 1, 2, 1, 2. And the mapping rule they give this time is 1/2 x and 1/2 y. So that means in this case, this line's pretty long, but because the mapping rule says 1/2, the line's going to end up being half as long, but not necessarily in the same place. So I'm going to take 6 and multiply it by 1/2. That's going to give me 3. I'm going to do 4 and I'm going to multiply it by 1/2. That's going to give me 2. So 1, 2, 3, 1, 2. So let's say here. This, if I multiply each of those by 1/2, I get negative 1 and 1. So negative 1 and 1. So there's the point. Half as long. All right? Seven. I think I'll just talk through 7 and 8 because they're the same. So in number 7, the point is at negative 1 and negative 1, and the other point is at 1 and 2, and they want you to multiply both of them by 3. So the new E point, the E prime, would be negative 3 and negative 3, and the F prime would be 3 and 6, because I just go across and multiply all the numbers by 3. Just make sure you know how to put those in the correct place on a graph and that you're labeling them. Number 8, same thing. G is 9 and 3, H is negative 6 and 0. You multiply each of them by 1/3. So for G, 9 times 1/3 would be 3, and 3 times 1/3 would be 1. So the new point would be at 3 and 1. For h, negative 6 times a third would be negative 2, but 0 times a third would still be 0. So the y value would not change. It would still be 0, but the x value would be at negative 2. So we've already done all those. That's how fast this is going to go. All right. Number 9. Says you have vertices at 2 and 3. 1, 2, 1, 2, 3. 2 and 3. That's point R. Point S is negative 1 and 4. 1, 2, 3, 4. And point T is negative 3 and negative 2. 1, 2, 3, 1, 2. So there we go. And again, I expect, wow, I can't play connect the dots. I expect you to label it R, S, and T so that I know that you understand where that all goes. They want you to do the mapping rule 3x, 3y. So they want you to take your xy points and go to 3x and 3y. In other words, just multiply everything by 3. So R prime, 2 times 3 is 6, and 3 times 3 is 9. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is R prime. Negative 1 times 3 is negative 3. 1, 2, 3. And 4 times 3 is 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So like up here, I'm sure. All right. And negative 3 and negative 2. Negative 3 times 3 would be negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And negative 2 times 3 is negative 6. 1, 2, 3, 4, 5, 6. So it ends up being, I can't get there from here, but it ends up being 3 times bigger. All right. The last one is the big one. And we will take it one step at a time. That's number 13. And I got you to do A through F, I believe. Which is not all of them, oddly enough. All right, I got you to do 13A through F. So for number 13, the first thing it asks you to do is draw PQR on grid paper or graph paper. So I don't have graph paper, so I'm freehanding it. So negative 2 and 2. 1, 2, 1, 2. That is P. Q is negative 2 and negative 2. So 1, 2, 1, 2. That is point Q. And R is 2 and negative 2. So 1, 2, 1, 2. So here's connect the dots. Okay. And that would actually be a right angled triangle. Now, it says calculate the area. So we're going back a chapter. So area of a triangle is base times height divided by 2. So here's the base. All you have to do is figure out how many squares across is that. To go from negative 2 to 2, that is 1, 2, 3, 4. So the base is 4 across, and the height is 1, 2, 3, 4. That's how tall it is. Because it's a right angle, I can just count. So 4 times 4 divided by 2. Well, 4 times 4 is 16, and 16 divided by 2 is 8. So the area for the black triangle is 8. And units squared, centimeters squared if you're using centimeters graph paper. Now it says find the image under the mapping 3x, 3y. So it gives you, it looks like this. So it just wants you to multiply everything by 3. So if I do that, this point is going to be 6 and negative 6, because I just multiply those. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 and negative 6, that is r prime. For this, it would be negative 6 and negative 6. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So this would be negative 6 and negative 6. That would be q prime. And this would be negative 6 and 6. So 2, 3, 4, 5, 6. That would be p prime. So that I still have a right angle triangle. It's just 3 times bigger than the one I had before. And now they say, this is D, calculate the area of this one. So area is base times height divided by 2. So the base, how far across is the base? Well, if I count squares, or if I know I'm going from negative 6 all the way to 6, that is a distance of 12. And height-wise, that is also a distance of 12. I'm going from negative 6 to 6. That is 12 squares. That is 12 units divided by 2. So 12 times 12 is 144. And 144 divided by 2 is, 144 divided by 2 is 72. So here's what I want you to notice. The object is 3 times bigger, okay? The object is 3 times bigger. So it's 3 times bigger. The area is 9 times bigger, right? Because this is 8, this is 72. If you do 9 times 8, you get 72. Think about the units for a triangle. It is centimeters squared. It is meters squared. It is units squared. Area is always a squared unit. So if you know the scale factor, if you know by how much you've increased the size, if you take that scale factor, and because we're talking area, and area is a squared unit, if you square 3, you get 9, and you know what you should multiply the original area by. 8 times 9 would be 72. Don't worry if you don't get that right away, because I'm not going to ask you anything like that. But next year, there's a section that's going to deal with that. So, and it's going to talk more in depth about that. So that's why I mention it now, so that maybe next year when Mr. Keynes talks about it, assuming Mr. Keynes is the one teaching it, you can go, she talked about that, she said something. The last 2 questions, E says find the image under, and we'll do this in a different color. It says, now take the black one, take PQR. So just take your regular XY. This time, do 1/2 X and 1/2 Y. In other words, cut it in half. So if I do negative 2 times 1/2, I'm going to get negative 1. Same thing here. So it's going to be negative 1 and negative 1. This is going to be 1 and negative 1. And this is going to be negative 1 and 1. So that triangle is half the size of the black one. So again, it says calculate the area. So area is base times height divided by 2. Now, before we do this, just so that we're hopefully putting things together. Here we took the scale factor and we squared it so that we knew if 3 squared is 9, then 8 times 9 should be 72, and that's what the area is. If we take a half and we square it, that's actually 1/4. You can check in the calculator, but trust me, 1/2 squared is 1/4. So if I take 8 and I multiply it by 1/4, I get 2. So let's see what actually ends up happening here. The base is 1, 2 across, so the base is 2. The height is 1, 2 up, so the height is 2 divided by 2. 2 times 2 is 4. 4 divided by 2 is 2. What did I say it should be? 8 times a fourth is 2. I can do it either way. It just gives you another way to figure out the area without having to do the area formula. That's all. All right, that's the homework. Section 8.5 deals with symmetry. Symmetry is just the idea that things look the same on one side as they do on the other. It is symmetrical. We see symmetry all the time in the world. God seems to like symmetry, and we as humans love symmetry. I don't know if you've heard about the golden ratio. If you haven't, I encourage you to go to YouTube and look it up. It's really cool. If you haven't heard about the golden ratio and how that all works, it's really amazing. And when you watch it, I'm not sure how you say that God didn't design stuff, because it's incredible. But the golden ratio has to do with like a spiral symmetry, but we're going to deal with even easier symmetry than that. Symmetry is just when it looks the same on one side as it does on the other. That's one type of symmetry. And then there's something else called rotational symmetry. So I'll talk about those both separately. So first off, there is reflectional or mirror symmetry, lines of symmetry. So if you have, if you have a rectangle, and if I was to draw a line directly vertically through that rectangle, it's the same on this side as it is on this side. That is called a line of symmetry. This one is a vertical line of symmetry. I could draw it horizontally as well, and it's the same on the top as it is on the bottom. So a rectangle actually has two lines of symmetry, okay? Some people want to tell me that in a rectangle, this is a line of symmetry. It's actually not, because think of a line of symmetry as like a line you would fold something on, and when you fold it would meet up exactly. With a rectangle, it doesn't usually meet up exactly. With a square, yes, but with a rectangle, no. So on a rectangle, there's more than one line of symmetry. Sometimes there's only one. Sometimes there's more than one. Sometimes there's more than 2 or 3. So if you have, and I won't do this well, if you have something like this, and let's say it was perfect, but it's not, but let's say it was perfect, and I said, how many lines of symmetry are actually here? There's actually 4. And you can usually tell when something has sort of like lobes on it, because the amount of lobes that there are is kind of the amount of lines of symmetry there are. Because I could draw one here, and it's the same on the left as it is on the right. I could draw one here, and it's the same on the left as it is on the right. I could draw one here, and it's the same. You've got these 2 lobes, and you've got these 2 lobes. and I could draw one here. So there's actually 4 lines of symmetry on that, okay? There is also something called turn symmetry. Turn symmetry is when you can take the shape and turn it, and it looks exactly the same. So, for example, they do one of those block letter I's. If we were talking about this in terms of turn symmetry, okay, there would be it's when you're talking turn symmetry, it's called the order of symmetry, and it just means how many times can I turn it, and I can't tell that I've turned it. It looks the same. So you can have this right side up, but if I flipped this upside down, it would look exactly the same as if it's right side up. Okay, so this is this has a turn symmetry of 2, because there are 2 ways to look at this where I can't tell the difference. That's what turn symmetry is. So let's go back to the ones where I drew lines of symmetry. In terms of turn symmetry, there are 4. The turn symmetry has an order of 4, because if I put this lobe on the top, or if I put this lobe on the top, or if I put that lobe on the top, or if I put that lobe on the top, you wouldn't be able to tell the difference as long as they're all equal. You wouldn't be able to tell the difference. That's as hard as this gets. Oh, I'm not kidding. That's as hard as this gets. If something has a turn symmetry of 2, in other words, there's only 2 ways this one looks the same, right side up or upside down. It has a turn symmetry of 2, turn symmetry of 2. Whenever something has a turn symmetry of 2, there's a word for that. It's called having point symmetry. It's called having point symmetry. All right, that's it. Honestly, that's as hard as this gets. So there is lines of symmetry and there is turn symmetry. That's it. That's all you need to know. For homework, one of the questions I'm going to give you says, print the capital letters of the alphabet. There's a homework problem for you. Print the capital letters of the alphabet. Do them like when you're in kindergarten in grade 1 and they teach you to do them really properly. That's what you're looking at, okay? So if I look, there's A, there's B, there's C, there's D, actually D should, like D, there's E, okay? It says print the capital letters. Which letters have vertical lines of symmetry? Meaning if I do a vertical line, it looks the same on the left as it does on the right. It appears to me that A does have a vertical line of symmetry. B, not so much. No to B. So all I want to know is which ones have a vertical line of symmetry in A through Z. And then they want to know which letters have a horizontal line of symmetry. So this time you go through the alphabet, and instead of drawing a vertical line, you draw a horizontal line. Not really the same on the top as it is on the bottom. So A would be a no. B would be a yes, because those 2 loops should be the same size. But I am not a kindergartner and I can't draw my letters properly anymore. But it should be the same on the top as it is on the bottom. So B, yes, has a horizontal line of symmetry. Then it wants to know which letters have both vertical and horizontal lines, which have both, and which of the letters have point symmetry. In other words, look the same right side up as upside down. Well, that would be a no, that would be a no, that would be a no, that would be a no. If I turn that upside down, then it looks backwards. So I would think that would be a no. Unless, maybe look in the back of the book and see what they say. But do they mean if I flip it upside down, it still does that? Like if I just flip it that way? Because maybe it does. All right. So again, you can turn it upside down and it looks the same upside down as right side up. I'm just looking to see what they say. I'm curious about that one. This is 8.5. Don't forget the answers are at the back of the book, and you should be checking your answers at the back of the book for anything that's not graphing. That's why I do the graphing ones on the board and leave you to be checking the other ones. If you're not checking, that's on you, all right? 8.5, let me see, D? Yeah, no, they say E does not have turn symmetry. So they're saying if I take it and I literally rotate it 180 degrees, well, now it's going to be like that. That's not point symmetry. So E is a no. All right. So you can check that you need to do those. So I will list the questions that I want you to do for homework. There's not that many of them. Probably some pretty easy homework, to be honest with you. This actually leads us to the end of chapter 8. So tomorrow we'll be doing a review. Monday will be a study day, and Tuesday will be a test. So Tuesday morning at 8:30, be there uploading the test, doing the test. You'll have until 9:40 to finish it and upload it to me like we've been doing. All right? And then we really only have one chapter left. So we're really close to the end of this textbook, guys. So have a good day, and I will talk at this camera again tomorrow.